I'm Michelle Morgan with Moeller Engineering, and I'm here today with Grace Sauger from Moeller Engineering and Callie Wegren with CDOT Region 4 to discuss with you how we, collectively, water resource engineers, commonly approach hydrology and how a particular project challenged this team to take a deeper dive into the hydrologic methodologies at our disposal and work collaboratively with the project stakeholders to make the best and highest use of project dollars. The project is Colorado 7, more commonly known to us as Colorado 7 Lower. It extends from its intersection with Colorado 72 on the west to the town of Lyons on the east. This is the final permanent repair project on the 2013 flood recovery effort that began 8 years ago, almost to the day, to repair damaged state highways and bridges after this historical event. As you can imagine, after spending hundreds of millions of dollars on over 400 miles of impacted roadways and more than 120 impacted bridges, the remaining funds for this project are limited. The project corridor has 137 cross culverts that convey runoff from the north side of the road to the South St. Vrain Creek on the south side of the highway. Given the limited funds and the constructability constraints of working in a canyon, we couldn't repair all the culverts in the 14 miles. So where did we begin? We began with an understanding of some of the key project goals: to maximize safety, minimize the inconvenience to the public, and to provide added road resiliency. With these goals in mind, we started where we typically start: the hydrology. The hydrologic problem we all face. How do we estimate the one peak design flow for sizing of the various hydraulic features? We all know that 10 drainage engineers could be given the exact same information for a drainage problem, and they would all get 10 different flow rates. We also know that all 10 flow rates could be considered correct. This is because there are an infinite number of combinations of the variables within the watershed that we have to try to estimate to arrive at the one peak design flow. Therefore, it is important that we start with asking ourselves the right questions. Does directly applying acceptable hydrologic methods translate to acceptable results? Not every accepted method is always too high. We could be too low. And how do we know? Are we making the right decisions to achieve the project long-term goals? What are the consequences of over or underestimating the design flow rate? The solution lies in collaboration with project partners. We met with CDOT and our project partners to discuss the available resources, such as flood photos, damage assessment reports, flood studies, CDOT maintenance inspection reports, and a meeting with CDOT maintenance to identify problematic areas. We also conducted numerous field visits with the project team. This process helped us sharpen our hydrologic analyses, review the results of the various analyses with the team, and work to avoid high and low design flow rate extremes. It helped us produce results we ultimately viewed as reasonable, thus allowing us a degree of confidence that we are sizing the culverts to best serve the project goals while balancing constructability and budget constraints. CDOT was facing a similar problem with hydrology on another project that helped bring perspective to our project. I'm going to turn it over to Callie to explain.
Thank you, Michelle. When CDOT received the initial hydrology results for Colorado 7, red flags were raised. Both Moeller and CDOT were questioning results in regard to constructability, budget, and resiliency. It was through these conversations and questioning that prompted our South Program resident engineer, Brian Varela, to look into the hydrology. He noticed that some of the hydrologic parameters were very conservative. For example, the rock outcropping curve numbers seemed really high. This sparked the connection to use similar methods as we had just done on an in-house project. Brian and I built 19 hydrology models in CDOT Region 2. With the help of Mueller's subcontractor, Derek Rapp, we did a reevaluation of our hydrology methods. Derek helped us to plot our hydrology results versus the 2013 flood data. Our data is in blue and the 2013 flood data is in orange. Although the 2013 flood did not happen in Region 2, both are geographically similar and we should expect more similar results. We did a sensitivity analysis of hydrologic parameters and re-ran our hydrology models. This was an updated hydrology, and as you can see, our results are more in line with the 2013 post-flood data. This exercise calibrated our data and increased our confidence in the results. Brian realized we could apply the same methodology to the Colorado 7 project. We encouraged Mueller to do a complete comparative hydrologic analysis and use the 2013 post-flood data as comparison. I will now hand it over to Grace, who will go into the details of the Colorado 7 analysis.
Thank you, Callie. For Colorado 7, we calculated our initial hydrology numbers using accepted hydrologic methods per CDOT's Drainage Design Manual. We used the rational method for basins under 40 acres and HEC HMS Snyder over 40 acres, pulling soil and rock outcrop data from NRCS. We used the initial hydrology results to assess if the existing culverts had adequate capacity to convey the 25-year design storm. Our calculations were showing the need for drastic upsizing, even to the point of showing large concrete box culverts to replace the current 24-inch cross culverts throughout the project. This seems strange, especially when the conclusions did not line up well with the flood damage in 2013. It quickly became apparent to us that our initial hydrology was too conservative, and we would need to dive deeper and refine our methods and assumptions. We discussed our initial findings with CDOT to decide on our next move. As Callie mentioned, we came to the conclusion we should start by conducting a comparative analysis between our hydrology and other projects and studies within the St. Vrain watershed. Specifically, we compared the 2013 post-flood study, the SIR regression model, and adjacent projects. Here is our initial hydrology in blue on a log scale discharge versus area graph, along with the 2013 post-flood data in orange and the SIR regression model in black. These studies confirmed our suspicion. Our initial results were indeed high. As you can see, while the orange line for the flood data crosses the y-axis at 80 CFS, our initial hydrology crosses at approximately 1,000 CFS. However, this graph also displays another fundamental fact. You can see the 2013 post-flood data cluster is calibrated based on much larger basin sizes, while most of our data deals with much smaller basin sizes. For a point of comparison, the 2013 post-flood data had about 9 basins. For the exact same stretch of road, we have 137 basins for. The issue of scale arises because flood studies and regression models are calibrated to rainstorms with long durations that fall over huge watershed areas. But with culvert hydrology, you have a higher intensity over a smaller area, so the unit discharge will be higher. For this reason, both the orange and black methods are too low for smaller culvert subcatchments and cannot be directly applied in our situation. So the next step was to study and refine our input parameters. We discovered that as far as dialing in specific basin parameters, the impact of understanding how rock outcrop in the canyon behaved was unparalleled in its influence on refining our hydrology. Derek Rapp created this hand-drawn graphic as part of the 2013 flood study, and we wanted to show it here unaltered. The red line is the theoretical hydrograph, and the blue line is the recorded data from the 2013 flood. The first item to note is that when the 2013 study backed into the hydrograph that best fit the data, they found that the best fit curve numbers actually showed no presence of rock outcropping, which tells us that the rock outcrop is not behaving like pavement as we had originally assumed, but in fact is negligible as far as the curve number is concerned. The second item to note is that the study also found the reason the receding limb is higher than expected is because the rainwater is draining into fissures and cracks in the rock and taking a day or 2 days to drain out and be seen by the receiving culvert or stream. In this way, the rock outcropping is acting a little bit like a sponge or even a detention basin, delaying that timing beyond the peak. We refined our land use and timing parameters based on fractured bedrock acting less like concrete than we had anticipated. For most of our data, we simply updated the refined parameters and were able to arrive at reasonable flows. Our parameter adjustments worked really well for basins under 160 acres, but there was a seeming disconnect on the upper end of our data as our watersheds got bigger. The larger the watershed, the closer we wanted to be to that post-flood calibration. So we used one last technique to bridge this transition area, averaging HEC HMS Snyder and SIR methods for the largest basins in our data set. So the original hydrology in blue is definitely too high. The flood hydrology was too low. Ultimately, we refined our parameters, disregarded bedrock, and arrived at acceptable final hydrology results, shown in green. Now, where the orange line crosses the y-axis at 80 CFS, our green line crosses at 300 CFS instead of the original 1,000 CFS of the blue line. With refined hydrology that reflected our specific watershed conditions and paralleled flood data, we were able to proceed with rerunning hydraulic analyses with confidence. Updated culvert calculations yielded fewer undersized culverts, reducing our total number from 41 to 29, but perhaps even more significant, resulting required culvert sizes were much smaller. Originally, nearly half of the proposed culverts were double cell or single cell CBCs or pipes 48 inches or larger. Updated culvert sizing only called for one new CBC and 2 pipes 48 inches or larger, with all other upsized pipes being smaller than 48 inches in diameter. One culvert story to end on. Shown is a picture of an existing 8-foot by 5-foot CBC with lovely vegetation drawn on the wing walls and our friend Alien living inside if you look closely. Original hydrology showed the need for upsizing this to 2, not 1, but 2 10-foot by 6-foot CBCs. However, since there was a significant rock outcropping within this basin, our refined hydrology numbers were able to reveal that the culvert does have adequate capacity and would not be a strategic use of taxpayer money to upsize. I'd like to turn over the presentation back to Callie to bring us to our conclusion.
Thank you, Grace. In summary, we had a few key takeaways from this project. First, as CDOT, we encourage you to challenge us. We realize on some projects we need to meet criteria and we have certain constraints. Moeller encouraged us to dive into the initial results which prompted this hydrologic innovation. The teamwork and communication led to successful design that balanced resiliency and constructability of the project. Refining the hydrologic methods resulted in culvert sizes that served the goals of resiliency of the canyon while being constructible and within budget. Last but not least, we were able to stretch the public dollar. This innovation resulted in cost savings that could be used in other aspects of the project. Since this was the last flood recovery project, it was critical to strategically use taxpayer dollars. This project is starting construction this month, and hopefully in a year you will be able to drive this corridor and see the design come to life. We appreciate your time today, and thank you for joining us. I also want to point out our friends in the picture. On behalf of all my fellow CSU alums, go Rams!